NVIDIA did not see it coming. In 2013, Google's data centers ran the math on a future where neural networks ate every GPU they could buy. The conclusion was clear. NVIDIA's silicon was not going to scale with the workload. 2 years later, Google was running custom AI chips. 10 years later, those chips train Gemini, serve search, and now ship in pods of 9,000. The actual semiconductor industry view is that the most important AI chip not made by NVIDIA is Google's TPU. It is the first hyperscaler ASIC to prove the model, and every custom chip that came after it is a copy. This video is the architecture, the supply chain, and the company that wins quietly behind the scenes. To understand why TPU works, you first have to understand the problem GPUs were never built for. A GPU is a graphics processor pretending to be a math accelerator. It carries caches, branch predictors, scheduler logic, and dozens of subsystems designed for irregular work. None of those are needed for a transformer forward pass. A transformer is a fixed sequence of matrix multiplications and a softmax. The compute graph is identical for every token. The dimensions are known at compile time. There is no branching, no irregularity, no reason to spend silicon on flexibility. Google's bet was simple. Strip the GPU down to its math core, surround it with massive memory bandwidth, and connect thousands of these stripped-down chips with a network designed for one thing: collective operations across the entire pod. The result is a chip that costs roughly half what a Hopper costs, draws roughly 2/3 the power per flop, and is delivered to a single customer at a single price. No CUDA tax, no NVIDIA margin, 10 years of compounding cost advantage. The heart of every TPU is a systolic array. Think of it as a grid of small, multiply-accumulate units, arranged so that data flows through the array like a wave. A weight enters from one edge, an activation enters from another edge, and as they meet inside the grid, multiplications happen and partial sums propagate to neighbors. By the time the data exits the far edge, an entire matrix multiplication is complete. The original TPU V1 had a 256 by 256 systolic array. That is over 60,000 multiply-accumulate units operating in lockstep. The memory access pattern is perfectly predictable. The control logic is trivial. There are no caches because data is reused as it flows through the grid. There is no scheduler because the compiler decides ahead of time what flows where. Compare that to a GPU. A Hopper streaming multiprocessor has a tensor core, a scalar unit, an L1 cache, a register file, a warp scheduler, and so on. Each one is silicon spent on irregular workloads. On a transformer, 95% of the flops come from the tensor cores. Everything else is overhead. The TPU's design philosophy is that overhead is the enemy. Every transistor not doing matrix math is a transistor not earning its rent. Newer TPU generations have moved to multi-chip module designs and 3D HBM stacks, but the systolic array stays at the center. It has been validated across 7 generations, and no one has built a better matrix engine yet. Single-chip performance is irrelevant for frontier models. The number that matters is how many chips you can wire together at full bandwidth. NVIDIA's answer is NVLink, then NVS switch, then InfiniBand or Ethernet beyond a single rack. Each layer adds latency and asymmetric bandwidth. Google's answer was something nobody else had built: an optical circuit switch fabric. Inside a TPU pod, every chip is connected to optical transceivers that talk to a central optical switch. The switch routes light between chips using tiny mechanical mirrors, micro-electromechanical systems, or MEMS. There is no electrical conversion in the path. Bandwidth between any two chips in the pod is symmetric, and the topology can be reconfigured in software for different workloads. A TPU V4 pod connects 4,000 chips. A V5P pod scales to nearly 9,000. The Ironwood pod, announced at the latest hardware reveal, runs 9,216 chips as a single training domain. To put that in perspective, NVIDIA's largest single domain is 576 chips on a Blackwell rack. Google is running an order of magnitude bigger, on light, with no off-the-shelf component in the path. The OCS fabric is the closest thing to a TPU secret weapon. Cisco does not sell it. Arista does not sell it. Broadcom does not sell it. Google designed and manufactures the optical switches in-house, with MEMS components from Lumentum and Coherent, two American optical specialists you have probably never heard of. This single architectural decision, made in 2018, is what lets Google train models that need 9,000 chips communicating in lockstep without melting their networking budget. Hardware without software is a paperweight. NVIDIA's CUDA stack is the most cited reason no one can dethrone them. Google's response was XLA, Accelerated Linear Algebra, a compiler that turns high-level math into TPU native code. XLA is built into every major framework. TensorFlow has used it since 2017. PyTorch supports it through PyTorch XLA. JAX, Google's research framework, was built XLA first from day one. This means a JAX model written for a single chip can run on a 9,000-chip TPU pod with one annotation change. CUDA cannot do this. The hidden cost of CUDA is that scaling beyond a single node requires rewriting parts of the model. Partitioning, communication, sharding strategy. XLA does this automatically through a feature called GSPMD, General Sharded Parallel Matrix Decomposition. The compiler reasons about the model topology and emits the optimal collective operations. For frontier model training, this is the difference between a 6-month engineering effort and a 2-week one. The trade-off is that XLA only targets TPU and a few other accelerators. There is no community ecosystem. There is no third-party support. If Google decides not to optimize for your workload, you have no recourse. But for the workloads Google does care about, large transformers, sparse models, mixture of experts, XLA is the cleanest path from research code to running silicon. JAX has quietly become the standard for academic AI research. CUDA still rules the GPU world. XLA rules the TPU world. They are converging. 7 generations. Each one solves a problem the last one revealed. V1 in 2015 was an inference-only ASIC for Google search. It was 28-nanometer silicon, low power, fixed function. V2 in 2017 was the first training-capable TPU and the first with HBM. It introduced the pod concept. 256 chips wired in a 2D torus. V3 in 2018 doubled the matrix engine and added liquid cooling. The pod scaled to 1,000 chips. V4 in 2020 was the inflection point. It added the optical circuit switch fabric, brought the pod to 4,000 chips, and was the first TPU widely used outside Google for cloud customers. V5e in 2023 was the cost-optimized variant for inference at GCP scale. V5p was the training flagship, the chip that trained the first generation of Gemini. V6, codenamed Trillium, shipped in 2024. Memory bandwidth doubled. Sparse core, a dedicated unit for embedding lookups, became standard. The chip was designed for both training and inference, but the marketing pivoted firmly toward inference economics. And then Ironwood. Announced at the latest Google Cloud event, Ironwood is the first TPU explicitly built for the inference era. 192 gigabytes of HBM3E per chip, more than NVIDIA's Blackwell. 9,216 chip pod. Architectural decisions throughout that prioritize tokens per second per watt over peak training flops. Ironwood is a statement. The AI workload is shifting toward inference, and Google is not going to let NVIDIA define how that workload runs. Each generation tells you the same thing. NVIDIA reacts to the market. Google sees the next phase 3 years out and ships hardware for it. The verdict. Google's TPU is the most strategically successful custom AI chip in the industry. It runs search, it serves Gemini, it is rented to OpenAI rivals through GCP, it scales further than NVIDIA can match, and it costs Google a fraction of what buying NVIDIA would cost. So who actually wins? 3 layers, 3 winners. First layer, Google itself. Vertical integration earns a structural cost advantage that compounds every generation. Gemini training and inference are roughly 30 to 40% cheaper than the equivalent OpenAI workload on Azure NVIDIA. That margin is now flowing into Google's AI margins. Second layer, the optical supply chain. Lumentum and Coherent ship the MEMS optical components inside the OCS. Without them, the TPU pod does not scale. As inference workloads grow, optical interconnect demand grows linearly with pod count. This is the dark horse of the AI hardware story, and we will spend an entire video on it. Third layer, and this is where the series narrative continues. Broadcom. From TPU v4 onward, Google co-designs the chip with Broadcom's custom ASIC team. Broadcom delivers the HBM controllers, the SerDes, and the design and verification work that gets each generation to silicon on Google's schedule. The published TPU is a Google architecture. The shipped silicon is a Broadcom platform. Every TPU dollar Google saves on NVIDIA flows partly to Broadcom. This is the same pattern as episode 6. Custom ASICs are a category. Broadcom is the IP layer underneath every winner in the category. Google is not the exception. Google is the first proof point. Microsoft Maya, Meta MTIA, AWS Trainium. Every chip in the next wave runs on Broadcom rails. To recap, NVIDIA does not own AI silicon. Google has been quietly running a parallel architecture for 10 years. The Systolic array is the heart, the optical fabric is the secret weapon, the XLA stack is the moat, and Ironwood is the inference era answer. 3 winners: Google's vertical integration, the optical supply chain, and Broadcom underneath it all. The next video in the AI supply chain series goes deeper into one of those 3. We are pulling apart Google's optical circuit switch, the MEMS technology that nobody outside Mountain View understands, the single architectural decision that lets the TPU scale to 9,000 chips, and the 2 American optical companies that benefit when every hyperscaler eventually needs the same fabric. If you want the actual semiconductor industry view of the AI race, not the press release version, subscribe. See you in the optical fabric video.